All right, so we've learned how to predict ions from electron configurations. And here we're going to look at predicting anions from electron configurations. It's really quite simple, and we really never need the electron configuration to predict ions, simply because we've learned that the location on the periodic table for the nonmetals, let me bring up our periodic table here, is enough. These locations here are enough to be predictive. The nitrogen we know wants to gain 3 to become like neon. Sulfur gain 2, right? Bromine gain 1 to become like their noble gas, nearest noble gas, right? But in terms of electron configuration, you can see how gaining those 2 electrons will fill the empty subshell. Okay? All right. Now, we get to talk about something that's a lot of fun. It's called Lewis structures. Lewis structures are structures that were invented, kind of a shorthand method of displaying the molecule. And it becomes very valuable because it can help us understand the shape of the compound, and the shape of the compound oftentimes will lead to understanding of the boiling point of the compound, boiling or melting point of the compound, the reactivity of the compound, the solubility of the compound. All right. So a lot of different properties can be understood simply by looking at the shape of the compound, because it is the shape of the compound that gives its properties, right? Structure of that compound results in the properties of that compound. Okay. It's just like little tiny Legos. They can do what they can do because of their shape. Some can bind this way, some can bind that way, but they have to have the right shape to do what their function is. So we have to be able to draw Lewis structures, we have to learn a few rules. Lewis structures for atoms are relatively straightforward and easy to learn, but that's where we start. We take an atom, whatever element it is, lithium, beryllium, carbon, nitrogen, whatever, and we surround it, that elemental symbol, by the number of valence electrons that element has. All right? Now, to get the number of valence electrons, you can use the electron configuration if you want to, but you can also just kind of look and see which column the element is in. And Lewis dot structures really only work for our representative elements. So we're not going to be dealing with any of our transition or our post-transition metals when we're forming Lewis dot structures. So because of that, it's really easy to look at the column, this being 1, column 2, column 3, 4, 5, 6, 7, and 8, and knowing how many valence electrons that atom has. So, how many valence electrons does nitrogen have, Fred?
Nitrogen? How many valence electrons? Let's see, it has what's the electron configuration?
Well, didn't we just say that we could do that, which its electron configuration is helium, 2s2, 2p3, right?
Okay, so it has 5, 2s2 and 2p5, 2p3.
Very good. But we can also now just count the column that it's in. And which column is it in?
Nitrogen?
Yeah, which column is nitrogen?
How do you count again?
This is 1, this is 2, this is 3, 4, 5.
So it's in the 5th column.
That's right, so that means it has 5 valence electrons. Very good. How many valence electrons does chlorine have in it then?
1, 2, 3, 7?
Yeah, that's right, 7 valence electrons. Very good. How about beryllium? How many valence electrons?
2 valence electrons for beryllium.
Very good. So again, this is just for our representative elements, but the number of the column tells us the number of valence electrons. Okay? Oxygen, 6th column, 6 valence electrons. And you see that the valence electrons are written around the atom in such a way that we identify or pretend like there's these 2 boxes on each side of the atom. Okay? So we don't want to, like Hund's rule before, we don't pair up atoms in valence electrons in Lewis dot structures until every side has at least 1. So it wouldn't be correct to do this. 1, 2, 3, 4, 5, 6 for an atom of oxygen. You have to go like this. 1, 2, 3, 4, 5, 6. Now, it doesn't matter if the two are, in case of oxygen, the two that don't have a full Lewis dot side, right, are here, or whether they're here or anywhere, because you could take this atom and kind of rotate it in any direction and think about it as being the same thing. Okay? So, for our metals, sodium, you form an ion, a Lewis dot structure, simply by removing that electron and making these brackets and putting a positive charge. And you can do that when oxygen forms an anion by putting those two extra electrons in and putting brackets and putting a negative charge. But Lewis dot structures aren't helpful for atomic or ionic compounds. Lewis dot structures don't have their power when we're talking about ionic compounds. The Lewis dot structure really just reiterates what the chemical formula of an ionic compound is. So Lewis dot structures are not helpful for ionic compounds. Where Lewis dot structures really have their strength is with molecular compounds. Okay, so the chemical formula, the ionic formula for, or the chemical formula for ionic compounds is just as effective as the Lewis dot structure. Okay, for covalent compounds, when we draw a Lewis dot structure, we follow some simple rules. We arrange atoms that are in the compound around a central atom. So we want to identify what the central atom is. We want the sum of all of the valence electrons to be represented on the compound. So we always sum up the valence electrons from all the elements that are in the compound. We bond all the outer elements to a central atom. For this class, we always deal with kind of small molecules, and recognize that these are for molecular compounds, because we said that the Lewis dot structure is going to be helpful for understanding how nonmetals come together. And then we call them covalent because they have similar valency. They all like to kind of gain electron density. We want to complete what's called the octet around the central atom. And that's what we've kind of shown already, where we have a central an atom's elemental symbol, and then there's like 8 regions of electrons, 4 regions of electron density with 8 specific electrons. Okay? So, we want to complete that octet when we're making these Lewis dot structures. And then we want to distribute electrons so that we can provide enough electrons for everybody to have as many electrons as they brought to the molecule. Okay? So, let's try to practice drawing this structure. Nitrogen trifluoride. All right? Now, I like to think of these, and it helps me kind of remember the rules, if I think of these atom or molecules as parties.
Parties?
Yeah. And the nitrogen and the 3-fluorine are coming together to a party.
Okay.
And in that party, everybody's bringing some refreshments. The nitrogen is bringing some refreshments. That's their valence electrons. Each of the fluorine are bringing some refreshments. That's their valence electrons. And we need to take account of how those refreshments are distributed amongst the elements of the party.
All right. So, how many refreshments does nitrogen bring?
Well, how many valence electrons does it have?
Well, can you show me the periodic table?
Uh-huh. All right, here's nitrogen.
Okay, 5th column, 5 valence electrons.
Very good. So I say that nitrogen has 5 valence electrons, right? And I'll write that 5 down here. Nitrogen has 5. How about fluorine? Did you see on the periodic table?
I have it here. 7 valence electrons.
All right. So there's 3 fluorine. All right. So I can say that each one of them brought 7 valence electrons. So that's a total of 26, is that right?
Yeah, 26.
So that's 26 valence electrons that are at this party. Now we try to identify a central atom, all right? What do you think the central atom might be here?
I don't know. How can you tell?
Well, usually it's the one that there's the fewest of.
Oh, you mean like nitrogen?
Yeah. So if we choose our nitrogen, and that's the first step, identify the central atom, and then we bond all of the other atoms to the central atom. All right. That's the next step. And then we try to distribute our 26 valence electrons on the molecule. Okay? Now, let me draw nitrogen by itself here with its 5 valence electrons to start off with. 1, 2, 3, 4, 5. All right? And then let me draw fluorine with its 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Can you see how when these Lewis dot atoms come together, they're going to, I'm going to use X's for nitrogen's Lewis dots, and the dots for, I'm going to change these to X's as well for consistency. And then we'll keep the dots for fluorine. And you can see how there's kind of a fit here where fluorine is now going to be able to lend 1 electron to the nitrogen and borrow that electron density from the fluorine. Now the fluorine here has 8 electrons around it. Can you see that?
Yeah, I can see that.
Okay. We can redraw this as well to be an actual bond between the nitrogen and the fluorine, and then we can fill in the electrons like so. So now that bond actually represents 2 electrons. Can you see how that bond there represents these 2 electrons?
Yeah, I see that.
Okay. So when we see any bond, here we just cavalierly drew these bonds, but those bonds represent 2 electrons. Each one of those bonds represents 2 electrons. Can you see that?
Yeah, I can see that.
Okay, very good. Let's give ourselves a little more space here, and let's get back to where we were. We have 26 valence electrons, and we have nitrogen bound to 3 fluorine. We try to distribute those fluorine, or the ligands, the ones that are binding on the outside of the central atom, evenly. We try to distribute them evenly. But once I've drawn this, which I kind of call the skeleton molecule, right? It's just the only way we knew that was from the chemical formula, NF3. We knew that was going to be our central atom, and those were our outside atoms. The fluorines were the ones on the binding atoms on the outside. And then I drew bonds, but now I've used some of these valence electrons when I drew those bonds. Each one of these bonds represents how many electrons did we say?
2 electrons.
So that's a total of how many electrons already drawn?
6.
That's right. So I have 6 electrons that I've used up. So I have a total of 20 valence electrons left that I have to put on this structure, this molecule. Now, the first electrons that I'm going to add on are going to go on the central atom. All right. How many more electrons does the central atom need?
How can you tell what it needs?
Well, we say that every atom wants to have access to 8 electrons. That's our octet rule. Octet rule. All atoms want access to 8 electrons. All right? And this nitrogen has access to 1, 2. Every electron in a bond it has access to. That's the good thing about a bond, because fluorine also has access to those electrons. So nitrogen here has access to 1, 2, 3, 4, 5, 6 electrons. But it wants to have access to how many?
8?
That's right. So we need to put on 2 extra electrons like that. Those are called lone pair electrons. And now the nitrogen has access to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now I have to make sure I subtract that 2 and say that I have 18 valence electrons left. Remember, this 6 was from my initial bonds. This 2 was the 2 I put on there. How many electrons does this fluorine have access to?
8?
No, just those 2 right there. See that?
Okay, yeah, I see.
It only has access to whatever is bonded to it. So we need to increase the number of electrons that it has access to by using lone pairs. So it's going to take 6 electrons. And now that fluorine has access to how many?
I'm not sure.
How many does it have access to? Well, it has access to 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons.
Okay, I get it.
Now, how many electrons did that take?
6.
Yeah, I had to put 6 more on the fluorine. So now I only have 12 valence electrons left. And I can do the same thing to each of these. 6, 10, 11, 12. So I used up all my electrons. And now everybody has access to 8 electrons.
Okay.
Now, that's half the ball game, or maybe 3/4 of it. But the next step is to determine whether the structure we drew is legit, whether it really makes sense. And what that means is we look at how many electrons each atom has right around it. Not access to it, but right around it. All right?
What's the difference?
Well, that's a good question. The difference is fluorine has access to 8, 1, 2, 3, 4, 5, 6, 7, 8, but right around it, it has access to 1, 2, 3, 4, 5, 6. Sorry, right around it, not how many it has access to. And then we only count that 1 electron as how many it has right around it. So this fluorine has access to 8, but 7 right around it. Okay? So, this fluorine, how many does it have access to?
8.
How many right around it?
7.
Very good. This fluorine?
Same.
Very good. How about nitrogen? How many does it have available to it first?
5.
No, I said available to it.
Oh, available to it. Let's see. That's 8 still.
That's right. 1, 2, 3, 4, 5, 6, 7, 8. Now, how many does it have right around it? I think that's what you answered first.
Yeah, it has 5.
That's right. 1, 2, 3, 4, 5 right around it. So the nitrogen has 5 right around it, and each of the fluorines has 7 right around it. And that's also, consequently, how many electrons each brought to the party. Right? Everybody's fine with sharing your refreshments, but you want to make sure that you keep them close around you so you don't just be the only one bringing refreshments to the party, because that's the worst, right? You go to a party, you're the only one who brought refreshments, and you don't get anybody else's refreshments. Everybody just shares yours, right? So atoms, same way, when they come to this Lewis dot structure party, they want to have around them the number of electrons that they brought to the party. And they want to have available to them an octet. All right, so they all have access to 8, and they have right around them the number that they brought to the party. Okay, very good. So we identified the central atom. We made our skeleton structure. We counted up the valence electrons, 26. We made sure that we distributed those valence electrons so that the nitrogen got the octet first, and then the fluorine all got their octet, and then we made sure that everybody had the correct number of electrons, not just available to them, but right around them. Okay, good. This idea of having the appropriate number of electrons around them, right around them, is called their formal charge. And essentially what you're looking at is the number of electrons that they brought, their valence electrons, minus the number of bonds and unshared electrons. All right? Okay? So, the formal charge then is the number of valence electrons minus those values. So you can have a positive or a formal or negative formal charge. A good structure should have 0 formal charge on all of the atoms. If you don't have 0 formal charge, then you probably have either the incorrect structure or an unstable structure. If it is correct, it's unstable, or possibly a reactive structure kind of thing. Okay? Okay. Now these bonds, which form by sharing electron density between atoms, these Lewis dot structure bonds, are covalent bonds, and covalent is showing that this is a share of electron density. This is not one electron donating an electron completely to another. This is sharing. Again, covalent, same valency. All of these atoms over here, non-metals, want to gain electron density. So instead of a metal, which would like to lose, and a non-metal, which would like to gain, coming together to form an ionic compound, these are, again, covalent. They both want to, in the same valency, they both want to gain. Okay? This occurs when, you can imagine, again, our overlap of electron density clouds, and then electron density can be shared between two different atoms, like bringing two hydrogens together. You can also think of it as bringing hydrogen with oxygen, right? In water, forming water. Oxygen's electron density in its orbitals, right? Here's oxygen's orbital diagram. There's two of these 2p's that have room for electron density, and bringing the hydrogen electron density into overlap with those 2p's makes what we could think of as our water molecule. All right. So you can have an overlap between not just one set of electrons, but you can have an overlap of two sets of electrons. We call this a double bond, or a triple bond can also occur. All right. So these covalent bonds are overlap of electron density. And why this stabilizes the situation is because, again, the nucleus has access to more electron density. And you look at this plot of energy as two hydrogen atoms are brought closer together. So this is the distance of separation here. So out here, the hydrogen atoms are very far apart. But then as they come closer, the energy decreases and stabilizes. If you get them too close, the energy actually goes back up as the nuclei begin to repel each other. But there is a sweet spot there where the energy is maximized. Bonds don't just stay stagnant there. They're always constantly stretching, right? We've talked about that. So going back and forth here, our bonds will stretch, and so that distance will slightly change as the energy is stabilized. Okay? The dissociation energy then is the energy necessary to separate these hydrogens completely apart from each other. All right. Not all atoms share electrons equally.